Section: Introduction. In this section, we delve into the realm of artificial intelligence, where the challenge lies in keeping large language models, LLMs, updated with the latest information. Traditional methods involve retraining models on vast datasets, which is time-consuming and resource-intensive. An alternative approach is model editing, allowing for the modification of stored facts and the correction of inaccuracies within a model. Several methods like Rank 1 model editing, mass editing memory in transformer, and emit have emerged to infuse knowledge into models without the need for additional training. These methods, known as locate and edit algorithms, aim to optimize the preservation memorization (PM) objective by directly modifying specific knowledge-containing areas of the model. Our focus is on parameter-modifying model editing methods that do not require additional training. We provide a step-by-step guide on using model editing methods based on the PM objective for a new model, using Llama-3 as an example. We start by making edits on all Llama-3 to 8B layers to determine the layer that offers the best editing performance, balancing accuracy and preserving existing knowledge. Once the optimal layer is identified, we conduct single-layer editing experiments using different methods. We explore three types of edits: singular edits, batched edits, and sequential batched edits. Singular edits involve editing one fact at a time, while batched edits update multiple facts simultaneously. Sequential batched edits update batches of facts sequentially in the same model. Previous studies have focused on increasing the batch size to enhance editing capability, but this can lead to model degradation. We compare the performance of batched model editing with sequential batched editing and find that for Llama-3, sequential batched editing with a batch size of 1024 shows optimal scaling performance. This highlights the importance of sequential model editing for large-scale model editing and its potential in approaching continual learning. Additionally, we establish baseline experiments on Llama-3 models to set benchmarks for future research and provide a transparent procedure for the decision-making process during model editing. Moving on to the preservation memorization objective, it comprises a preservation term and a memorization term. The objective is to optimize the preservation and memorization of facts within the model. Methods like and optimize this objective using different constraints, leading to efficient memory edits with a single gradient update, known as batched edits. Model editing metrics such as efficacy score, S, paraphrase score, PS, neighborhood score, NS, and composite score, S, are used to evaluate the success of model edits based on factors like edit success, generalization, and locality within the model. These metrics provide a comprehensive assessment of the effectiveness of model editing. Section Summary. In this section, we delve into the challenges of keeping large language models, LLMs, updated in the AI field. We explore model editing methods like Rank 1 model editing and mass editing memory in transformer, which optimize the preservation memorization (PM) objective by directly modifying specific knowledge-containing areas of the model without requiring additional training. By comparing batched model editing with sequential batched editing on Llama-3, we find that sequential batched editing with a batch size of 1024 shows optimal scaling performance, highlighting the importance of sequential model editing for large-scale model editing and continual learning paradigms. Section: Finding optimal layer for model editing. In this section, we assess the effectiveness of hidden states in LLMs for recalling facts using causal tracing. We discovered that the subject's last token representation in the feed-forward networks at intermediate layers is crucial. Based on this, we propose treating linear layers as a key-value memory system to enhance memory recall by modifying values in effective hidden states. However, we found that layers important for causal tracing did not always improve model editing performance. To determine the optimal layer for model editing, we conducted 1,000 non-sequential edits on the counterfact dataset at each layer of the Llama-3 model. We evaluated the impact of these edits using various model metrics, including efficacy score, S, paraphrase score, PS, and neighborhood score, NS. Layer 1 consistently outperformed other layers in Llama-3, similar to the findings in LLaMA2. After identifying the optimal layer, we performed large-scale model edits using batched editing. Editing multiple layers simultaneously could sometimes mask the effectiveness of model editing, so we focused on editing a single layer, layer 1, of Llama-3 with different batch sizes. We observed that larger batch sizes led to a decrease in model performance, particularly in the neighborhood score metric. To address this issue, we explored sequential batched editing, where we updated a batch of facts with one update and sequentially edited multiple batches at a time. By varying batch sizes from 1 to 4096, we found that smaller batch sizes were more effective in enhancing model accuracy and efficiency compared to larger batch sizes. Both methods, and Emmet, showed similar trends in optimizing model editing objectives.